Hello, my name is Andrew Thake. I'd like to welcome you to this Keynote Fireside chat with one of the world's leading battery metals experts. He is Professor Donald Sadoway, the John F. Elliott Professor of Materials Chemistry, Department of Materials Science and Engineering at the Massachusetts Institute of Technology. A warm welcome to you, Professor.
Thank you. Pleasure to be here.
I'd like to dive in with an opening generic question. How do you think lithium-ion batteries will develop over the next 5 years?
I think there are going to be some major changes. We see several trends. One is to improve the energy content per unit volume. And I think we're going to see a migration away from the carbon host for the anode to lithium metal, 100% lithium metal as the anode. And with that will come, I think, major changes in the chemical composition of the electrolyte. The electrolyte is the right now it's the liquid that lies between the two electrodes and forces the electron transfer reactions at the two electrodes. And I think because it has to be non-aqueous, it's an organic liquid and it's flammable and volatile. And I think people want to get away from that, make a battery that's got more energy density and also is not prone to fire. So I think we're going to see changes in the electrolyte. I'm sure the people viewing this have heard so much about the race towards solid state. What do they mean by solid state? They want to get rid of the liquid electrolyte and go with an all solid electrolyte and thereby have a battery that is not flammable. So I think those are two major trends: solid state electrolyte and lithium metal anode. I think those are two trends that we're going to see.
And just on the solid state batteries, when do you think we will be seeing them? Is it like in the next 1 to 2 years, the next 5 years? Because often we get a new technology and now it takes 5, 10, 15 years for it to become mainstream.
Well, you're absolutely right, Andrew. I think the big question here is not simply can we do this, but I think people who are responsible when it comes to, say, automotive applications want to have confidence that this is a durable technology that they can rely upon to perform over periods of years. And so there's going to have to be not only demonstration of the technology, but demonstration that the battery can cycle hundreds of times and continue to give the performance that people expect and so on. So I think it is a matter of years. I don't think it's 10 years, maybe closer to 4 or 5 years. Mm-hmm. But it's the reliability piece. You know, at some level, some people have said to me, well, Sadoway, you claim this battery can cycle and perform well over 10 years. Do you have 10 years of data to show us? And I think, wait a minute, that's a pretty tall order. So this is the sort of thing people are facing here.
Yeah. And just as in terms of the impact on the lifespan of these batteries, what do we expect to see when we go to, let's say, solid state? Is it going to be double lifespan? Is it going to be longer? Is it going to be even longer than that? Or is it how long is a piece of string? We're not really too sure yet.
I think a lot depends upon the rest of the chemistry of the battery. Certainly with a solid state electrolyte, some of the degradation mechanisms that we see with today's liquid electrolyte, those mechanisms will be disabled. So that means that should result in a longer service lifetime. But there are other reasons that the batteries today are failing, and they have to do with breakdown mechanisms that are operative within the electrodes themselves. Mm-hmm. And to the extent that changing the electrolyte, for example, if you go to lithium metal as your anode, then many of the breakdown mechanisms that are present in today's carbon host, those are taken off the table. So that could result in a longer service lifetime as well.
These changes in chemical composition, how would that actually impact the mining industry in the battery metal space? Because obviously in a lithium-ion battery, it uses lithium, it uses cobalt, it uses nickel, it uses graphite. What battery metals will become more important in this sort of next generation of lithium batteries?
Well, if we go to lithium metal, no question that it's going to be lithium. But lithium is metal, because in today's lithium-ion batteries, the presence of lithium metal is essentially vanishingly small. I mean, people are talking about lithium compounds. They're very focused on lithium carbonate, lithium sulfate, lithium chloride, what have you. They're not talking about lithium metal. But if we go to lithium metal batteries, that will bring lithium metal to center stage. Now, you mentioned cobalt. I mean, this all gets into the conversation about what makes sense for a long endurance cathode material. Today, it's the lithiated transition metal oxide, which is cobalt oxide, nickel oxide, manganese oxide. And of course, people are concerned about supply chains, about ethical sourcing, potential recycling, and so on. So yes, there will be a major effort at trying to see how, with the lithium metal as the anode, what are the radical changes that can be made in the cathode, which, let's be honest, people are working with great intensity to try to substitute cobalt out of the cathode. They want to have metals that are found under their own feet in their backyard.
And I mean, is that sort of like realistic, or like, can we just not do without cobalt?
That's a difficult question. There's no question that the presence of cobalt enhances the performance. Mm-hmm. And so people are trying to get the highest performance with the minimum amount of cobalt. Mm-hmm. And they brought the cobalt fraction down substantially, but cobalt-free you don't see. There are some efforts with the iron phosphate, which of course is cobalt-free. Mm-hmm. But iron phosphate, it has a lower level of performance. So this is a complicated multivariate optimization problem. And the question is, where is the sweet spot that will give something that is economically favorable, that appeals to the buyer, and is profitable to the miner? I don't know the answer to that just now, Andrew.
Sure. What about lithium sulfur batteries? What's your view on them?
Well, I've done some work on them myself. There, of course, we know that there are problems associated with sulfur. It's very cheap, and it would be a fantastic improvement in the cost of ownership. However, the sulfur is chemically active in today's liquid electrolyte, and this chemical activity results in parasitic side reactions, which then siphon off much of the efficiency of the battery. So there are clear challenges, but that's something that I intend to work on. But right now, there's nothing out there that can perform.
Sure. In terms of battery manufacturers, are there any particularly battery manufacturers that have caught your eye in terms of the EV innovation space? And if so, why? No. What are they doing?
No, I think when it comes to innovation, the manufacturers are focused on improvements in the manufacturing process to get the cost down, the reliability up. But when it comes to radical innovation, this is something that people are generally loath to embrace, because it's a big risk. It's a big risk, and especially if you're talking about battery manufacturing as applies to automotive applications. Anybody who's ever worked with the people in the automotive industry will know very well just how demanding these people are, how risk averse they are, how conservative they are. And So you don't walk into the automotive environment and say, how about something radical? No, no. They're saying, no, don't talk to me about 5 years of development. They say, give me something that I can buy off the shelf today and put in the car today. That's what I want. I'm not interested in some science project. So this, at some level, throttles innovation.
So where then does the innovation in the battery metal space come from? Does it come from academia such as yourself, or does it come from elsewhere?
I think the university is one place where you will see unbridled innovation. Then, of course, you know, in places like the United States, you have this vigorous startup culture where people with wild ideas can obtain seed funding and launch an initiative to try to demonstrate something that is audacious. But yeah, I mean, let's not forget that the lithium-ion battery itself did not originate in the battery industry at the time. At the time in the late 80s, the nickel metal hydride battery was the dominant chemistry. But lithium-ion didn't come because somebody who was manufacturing nickel metal hydride said, we can do better. No, the nickel metal hydride was deeply entrenched. And the lithium-ion battery came when Sony, which was a company that produced these handheld devices that would benefit from a superior battery chemistry, Sony launched the lithium-ion battery. So the reminder here is that radical innovation in batteries came from outside the battery industry. And I expect the same thing will continue to happen.
Okay. Before I got on the call to do this interview, I just sort of went onto Google and Googled sort of like next generation battery technologies, and I got a whole list of interesting phrases that came up. So I'm just going to run certain sort of like next generation battery technologies, and you can say whether they're going to be a hit or a miss, and if so, why, and provide some additional commentary. The first one that came up was nanobelt lithium tungsten.
What was the first term?
Nanobelt lithium tungsten.
Well, you can couple lithium with tungsten and there'll be a voltage and so on. But I think that's something that's rather in its infancy.
Okay. Zinc manganese oxide batteries.
Well, that's the primary battery that we use. That's the copper top Duracell. That's the disposable battery. That's a zinc manganese oxide. Those things are not rechargeable, because when you go to recharge zinc out of the manganese oxide, you run the risk of evolving hydrogen on the negative electrode, and then you'll have a bloating and an explosion and so on. So you know, this is the other thing, Andrew, that a primary battery is much easier to engineer because it only has to discharge. But the rechargeable battery, as the name implies, is bidirectional. Sometimes you discharge the battery, you draw current from it, and then at some point later, you want to recharge it. You want to restore the energy capacity that it held before you discharge the battery. So that's a more challenging problem, because all of the electrochemical reactions have to be bidirectional, and that raises the bar substantially.
Sure. Okay. I'm going to throw out one more sort of like phrase that I Googled, and you can just tell me what you think of it. Organosilicon electrolyte.
Okay, organosilicon electrolyte. I mean, I think that's a step in the right direction. In other words, people want to get away from something that's volatile and flammable. So it would be something like a silicone, siloxane, something like that. Can it be done? Possibly. Is it going to be cost effective? Will it withstand hundreds of discharges and charges? I'd have to read carefully to render an opinion on it. But I mean, I think they're attacking a correct problem, which is to get rid of the volatile, flammable electrolyte.
Sure. Yeah, I mean, it may be the case that there's a lot of these next generation battery technologies. They're at their infancy stage, but whether they ever go beyond sort of base one to base two, I guess that's really is the sort of question, really.
Okay.
Yeah. Are there any other battery technologies out there that have caught your eye that you think that after sort of solid state, it might be the next one to go and take a look at?
Well, I personally have been heavily invested in lithium-free technologies. There's this tagline, beyond lithium, and I don't mean lithium, sulfur, lithium air. I mean no lithium at all. And so if I had to look at what would be a major challenger to lithium, I would go after aluminium. Aluminium, it's far more abundant, 8,000 times more abundant in the Earth's crust than lithium is. We know a lot about the electrochemistry of aluminium, and I don't have to couple aluminium with things like cobalt oxide and so on. So I've got some skunkworks projects of my own, and I'm really keen to have solutions that will operate in, say, stationary storage, say small, medium enterprise, single family home, some hundreds of kilowatt hours on something the size of say a 25 cubic foot refrigerator, but also for automotive, something that will give you hundreds of kilometers on a single charge and absolutely no fear of combustion. And I think something that is cost effective and safe, there's a need for that. So yeah, that's what I'm working on.
In terms of obviously a lot of the use for these batteries is obviously in electric vehicles. What's your view on how the rollout of electric vehicles will go and progress over the next 10 years?
Well, I have some good news for some of the miners who are watching this. And I think one has to look at the rollout of electric vehicles in the context of the entire society. And we know that people are going to be dependent upon recharging. And this means it's not a matter of simply erecting a station that has the receptacle that will allow you to plug in. You have to have the infrastructure beneath the pavement there that can deliver adequate amperage. And so to the people who are involved with copper, I see a lot of copper in the future, because we're going to have to be able to bolster the delivery of electric current to be able to service all of the charging points. And so I think that the ease with which people can charge up their vehicles, I think, is going to have a big impact on the rate at which people embrace the purchase of electric vehicles and turn their backs on internal combustion. So I think that there's a clearer link to the mines.
We're certainly seeing an increase in electric vehicles here in the UK over the last 10 days, as you're seeing with our petrol shortages. But just on that, but just back to the infrastructure challenge, I would have thought that in terms of rolling out the infrastructure, maybe rolling out along the highways and the motorways is one thing that can be done relatively easily. But presumably the challenge is when it comes to sort of like country roads and rolling out of the whole sort of like network. Is it just going to be just like too kind of costly to let's say roll it out either the whole of the US or the whole of the UK or any other country that would choose, where it's a mixture of urban and country?
Well, there's two ways to deliver current to the charging point. If you can imagine at a petrol station where you have a plurality of pumps and you have maybe 10 cars side by side, each one of them with a hose and refueling. So how does that happen? How does it happen? We're not pumping petrol all the way from some refinery to some remote point on the highway. We have giant storage tanks of petrol, and we've got a pump there, and we're drawing on it instantly to recharge the vehicle. So it's my thesis that what we should do is to take the existing infrastructure and install batteries, large format stationary storage batteries that will serve as ballast, so that when the motorist arrives with his or her automobile and wants to charge rapidly, say over the period of 10 or 15 minutes, something like this, the current doesn't come directly from generating station tens or hundreds of kilometers away. It's coming out of a battery right there. And then after the battery's been depleted, it can slowly, over time, recharge and be ready for rapid discharge. So we use this as an intermediate ballast, and thereby become a little bit more crafty in how we're going to service all of the customers, as opposed to saying, well, we'll just put these gigantic cables, each the girth of our thigh, going for hundreds of kilometers. I mean, it's a ham-fisted approach, I would say.
Yeah. And this is one sort of like one or two final like wrap-up questions. If you were an investor, obviously, but you say that you are in your spare time an investor, and you were looking to invest in the battery metal space, where would you invest your money in and why? So, you know, it could be a battery metal, it could be a battery technology company, it could be a mining company, it could be an electric vehicle company, or it could be somewhere else. How would you sort of like invest?
Oh, Andrew, you're putting me on the spot. I'm a professor. I'm a professor of electrochemistry. Don't listen to anything I have to say about how to invest one's money. But I certainly would say I would look at new opportunities, but these are going to be risk. You know, there's looking at beyond lithium chemistry. I mean, I really like. I think aluminum battery chemistry is something to be proactive on. So and of course, if we're thinking about infrastructure, no question copper. No question copper. You're not going to be laying superconducting wire. Forget about that. We're going to be laying copper.
Yeah, it's certainly, you know, I've had numerous conversations with investors in 2021. I haven't yet met an investor that hasn't yet said to me that they're long-term bullish on copper. And I think on that positive note, I think it's just all it remains for me to do is to go and thank you very much for your time. That was Professor Donald Sadoway from the Massachusetts Institute of Technology. Thank you very much for your time, Professor.